Hello, all of you. So, today we will be talking about wave particle duality. As we all have heard that light has a dual nature, it has a wave nature as well as a particle nature. So, today we will be talking about this duality. So, we start with the historical perspectives. We start with Democritus, who postulated that atoms are void and all the phenomena that are taking place are due to the dynamics of these atoms. Later on, Aristotle said that there is no voids in nature, and all the matter is made up of fire, earth, air, and water. And it's a continuous process. The matter is continuous, there is no discreteness. Later in the 17th century, when we talk in terms of light, it was Newton who postulated a theory and said that it's a stream of corpuscles and different colors correspond to different corpuscles. And the number of the corpuscles gives the intensity. The intensity of light depends on how many corpuscles are there. So in a way, the color was different for different kind of different corpuscles, and the number of corpuscles define the intensity of light. And it was successful in establishing that has the ability to travel in straight lines and also satisfy the phenomena of reflection. Later, Huygens came with his theory that it is a continuous wave like sound waves, and different colors correspond to different frequencies. And the intensity are the functions of the strength of vibrations. The more intense the vibration is, the more intense the light. Later on, John Dalton came with his theory of periodic table, and he said that the structure of the crystal is due to the periodic arrangement of atoms. Later on, Maxwell Boltzmann gave their theory, which is a statistical theory, and they postulated the properties of gas through atoms. And heat energy is the random motion of the atoms. And which is also a result of the microscope. This motion is microscopic in nature. Later on, Maxwell came with his concept of electromagnetic wave. They were these equations, the Maxwell equations, were established on the earlier hypothesis given by Gauss, Faraday, and Ampere. So Maxwell's conceptualized and combined all these earlier concepts and gave a confined theory of light, which is uh, acceptable till now. And Young showed from his double slit experiment that there is a particle theory of light. So basically, before 1900, it was a classical physics, and it was believed that a particle travels in a trajectory with precise position and momentum at each instant. And any type of motion can be excited to a state of arbitrary energy. It can be have any values, and the energy is continuous. And the wave and particle are two distinct concepts. But this theory was not able to prove the black body radiation, the heat capacities of solids, photoelectric effect, diffraction of electrons, and some more. So a theory was required, a modification was required to counter these effects also. So considering the black body radiation, if we consider a radiation from a pinhole in a closed contained in a characteristic of the electromagnetic waves within a container, the theory was initially given by Waynes, who said that the product of the temperature and the wavelength is constant. And later on, Stephen Boltzmann came up with a modified theory that the emitted power is proportional to the fourth power of temperature. You can see that at the low, since it's proportional to the fourth power, so when the temperature is low, it's quite less. And as soon as the temperature is increased, it shoots up. And Rayleigh Jean's law came up with their concept of density of states, and the energy depends on the density of its state, which is a function of the wavelength and the temperature. This Rayleigh-Jean's law was quite successful at long wavelengths, but at short wavelength it fails badly due to the high frequency. As we all have seen here, light from the earlier concept, that light is a continuous process. There is no discreteness. But Planck in 1900 came with a concept that the energy of the electromagnetic wave is limited to discrete values, and these values are integral multiples of h nu, where h is the Planck's constant and nu is the frequency. So the energy is an integral multiple of h nu, and Planck gave his density expression for the density state. And since he talked in terms of the discreteness, he limited the values of the energy in terms of the integral multiples of h nu. So h nu is a definite quanta of energy. And it is the minimum energy that should be there. And all the other values will be integral multiples of it. So this theory was successful in explaining the black body radiation. And later on, the heat capacities of solids have been described by Dulong-Petit's law, which is state that the heat capacities are proportional to 3R. And Einstein made a correction in it. He considered that the oscillation energy of the atom is an integral multiple of h nu, not the energy, but the oscillation energy. So we can see that if there is any transition from the higher level to a lower level, there is an emission of a photon of energy h nu. So if there is an emission of one photon, the energy will be h nu. If there are two, it will be 2 nu, and so on. And this frequency will depend on the energy levels. If there is a transition between the level E2 to E1, then the frequency will be different. And if there is a transition from E3 to E1, it will be different. So the frequency takes into account the difference in the energy of the two levels, and all the total energy should be an integral multiple of it. That means the energy of a single photon is h nu. Nu depends on the difference in the energy level, and the total energy depends on the number of the photons emitted. That means the total energy will be integral multiple of h nu, because you can't have any fraction of a photon emitted. A photon is emitted as a whole. So this Planck's distribution agrees with the experimental results and accounts for the Wien's and the Stephen Boltzmann law. And it also says that the energy of an electromagnetic wave is quantized and should be discrete, but cannot be continuous. Discrete in the sense that it is an integral multiple of h nu. And now we have two hypotheses with us. The wave hypothesis says that light is an electromagnetic wave, frequency n and wavelength l. And the supporting effects are diffraction, interference, and electromagnetic waves propagation. Whereas on the other hand, we have particle hypothesis, which says that the light is a stream of particles called photons, And the quantities governing it are the energy and the momentum. And it supports the experiments of reflection, refraction, photoelectric effect, and other Compton effect and all. So ultimately, he probably said that we have two concepts now. Light travels as an electromagnetic wave. Like we were having two concepts, wave hypothesis and particle hypothesis. So when we combine these two concepts and we come to a conclusion that while traveling, light is an electromagnetic wave. And while absorption and emission, it behaves like a particle. And this particle travels like a wave. So this is a duality. While traveling, it is a wave. At the time of emission and absorption, it behaves like a stream of particles. And de Broglie in 1924 postulated that these particles behave like a wave and they have momentum, which defines the quantity of the particle, which is an attribute of the particle, and the wavelength is the attribute of the wave. And this was confirmed later on by experiments by Anton in 1999. So the momentum is equal to the mass into velocity is equal to h upon lambda of hc upon lambda. So basically, quantum mechanics originated when the classical physics failed to account for the existence of the discrete energies of atoms in their experiments, which came up in the early 20th century. And the total failures of the classical concepts paved the need for a correct theory. So a new mechanics was needed, which is the quantum mechanics, and has opened a new era of physics. So we limit ourselves here in this talk of wave particle duality. We will be talking about photoelectric effect in the next